The vast majority of chemical reactions take place in a solvent, which is a bulk liquid in which we dissolve the reactants so that they collide with each other on a regular basis as they move through a solution. It's tempting to think of the solvent as an innocent bystander in chemical reactions, and we often do this by, for example, not worrying about the solvent molecules in drawings like this. It's implied that the solvent molecules are kind of existing in the background. They're not the major players in the reaction, the reactants and products are. However, solvent can exert a huge influence on the rate and course of a chemical reaction through a suite or group of effects that we refer to as solvent effects. And solvent effects can largely be understood in terms of intermolecular forces, with the understanding that when the solvent solvates or dissolves a reactant molecule, it does so by engaging in intermolecular forces with that molecule. The types and strengths of these intermolecular forces can influence how that molecule behaves, and this is the essence of solvent effects. To understand solvent effects, we really want to answer the question, what do solvents do? What is their purpose in chemical reactions, and how can we envision the solvent's role on a molecular level? So solvent is the medium in which a reaction occurs, and it's almost always liquid, and the solvent molecules engage in intermolecular forces with the reactants, products, and all species in between. The solvent molecules are in such high concentration that they're always engaging with the reactants as they progress to products. For polar organic reactions involving charged intermediates, cations and anions, the role of the solvent is key in stabilizing these charged intermediates. These are molecules that can't exist in the gas phase. They'd be too unstable. It's intermolecular forces between the solvent and these charged intermediates that enables them to exist. More specifically, ion-dipole interactions, or even for polarized transition states or intermediates, dipole-dipole interactions. Take, for example, the SN1 reaction shown here. This reaction doesn't occur in the gas phase without a huge input of energy. Solvent quantities of methanol are required to get the reaction to go. And as we've seen, even in the presence of solvent methanol, the first step is still uphill in energy. How does the solvent actually participate in stabilizing the intermediates of the slow step here? Well, keep in mind that this carbon in the carbocationic intermediate is positively charged, while the chloride anion is negatively charged. Methanol is a molecule that can hydrogen bond and engage in dipole-dipole interactions, and the negative end of methanol's molecular dipole can engage in an ion-dipole interaction with the carbocation. In fact, a large number of solvent molecules can do this. I've just shown 3 here to illustrate the point that solvent molecules can engage with the carbocation in order to stabilize it. Of course, methanol has a positive end as well, and the partially positive hydrogen atoms of the OH group can also engage in ion-dipole interactions with chloride, stabilizing this ion. Visualizing and understanding these types of interactions are key to appreciating why, for example, what's called a Protic solvent, which we'll see in more detail here in a second, is great at accelerating the SN1 reaction, much more so than a solvent that's aprotic, something like THF, that lacks an OH or NH bond. The strong polarization of that OH bond is key to these intermolecular forces. In understanding how the solvent engages with the reactants, transition states, and intermediates of a particular reaction, there are really 2 key questions we need to answer. The first is, what intermolecular forces is the solvent actually capable of? This comes down to hydrogen bonding versus purely dipole-related forces. Solvents that can engage in hydrogen bonding are called protic. They're called protic because they have proton-like hydrogens attached to highly electronegative atoms like oxygen and nitrogen. Substrates that are incapable of hydrogen bonding are called aprotic. We can also ask a question about the relative strengths of intermolecular forces, and this comes down to the issue of how polar exactly is the solvent. How much partial positive or partial negative charge, as the case may be, is the solvent presenting to these ions? One measure of that is the molecular dipole. The one that's in more common use is the so-called dielectric constant, which we'll explore in more detail here in a second. In fact, the dielectric constant is a more direct measure of the ability of a solvent to support and separate ions of opposite charge, for example in a step like D sub n, the first step of the SN1 mechanism. In general, high dielectric solvents are polar and display stronger intermolecular forces in general, stronger hydrogen bonds for protic solvents and stronger dipole-dipole forces for aprotic solvents. Although we can't really put a clean cutoff on polar solvents are north of this number and nonpolar solvents are south of this number in terms of dielectric constant, to a rough approximation, greater than 20 corresponds to a polar solvent. All of the compounds you see here are considered polar solvents. Water is, of course, the textbook example. The second molecule is dimethyl sulfoxide, or DMSO. This molecule is dimethylformamide, or DMF. We also have methanol, ethanol, and acetone, which are common polar solvents. Nonpolar solvents tend to have relatively low dielectric constants and low dipole moments. These are things like dichloromethane, or DCM, tetrahydrofuran, or THF, diethyl ether, which you'll often see abbreviated as ET2O, and of course hydrocarbon solvents such as hexane are going to be squarely in the nonpolar territory. Notice that even some of these compounds that contain polar bonds, like THF and DCM, are nonetheless nonpolar on the whole because they have enough hydrocarbon built into their structures, THF is a good example of this, that on the whole they're nonpolar, despite the presence of polar bonds within the structure. Polar solvents tend to accelerate SN1 or E1 reactions by stabilizing the intermediates after loss of the leaving group from the starting alkyl halide or pseudo halide through the intermolecular forces that we saw on the last slide. Protic solvents are especially good at this. What exactly do we mean by a protic solvent? Well, a protic solvent can serve as a hydrogen bond donor. In other words, it has an oxygen hydrogen or a nitrogen hydrogen bond. Aprotic solvents lack these bonds. This is the same list of solvents from before, and we can survey this list to identify the protic solvent straightforwardly, looking for OH or NH bonds. Water is a classic protic solvent due to its two OH bonds. DMSO is aprotic because it lacks this key structural feature. So is DMF. Although DMF has oxygen and nitrogen, neither of these is directly connected to a hydrogen. Both methanol and ethanol, which contain the hydroxyl group, are of course protic solvents. And acetone, despite the presence of the oxygen, is an aprotic solvent. Nonpolar solvents are generally aprotic because the presence of an OH or an NH bond tends to lead to a polar molecule. And that's the case here. Thanks to their ability to engage in strong dipole-dipole interactions and hydrogen bonds with charged intermediates of reaction mechanisms, polar solvents will accelerate SN1, and we saw this in an example of the intermolecular forces involved on previous slides. Polar aprotic solvents, which are still capable of engaging in dipole-dipole forces, acetone is a great example of this, tend to accelerate SN2 more so than SN1 or E1. The reason for this is that polar aprotic solvents tend to engage in stronger IMFs with the cations that come along with anionic nucleophiles rather than the nucleophiles themselves. They engage in stronger intermolecular forces with the cation, often because their negatively charged atoms are located on the periphery of the molecule. Acetone, again, is a nice example of that. The oxygen is on the periphery, close to a point where the molecule is capable of engaging in an intermolecular force. This leaves the anion relatively naked and reactive. Protic solvents can actually slow SN2 because they engage in strong hydrogen bonds with anions like this. We saw an example of that involving chloride at the beginning of this video. And here's that general principle again, just restated. Protic solvents surround these strong nucleophilic anions very well, especially small anions like fluoride. This leads to an interesting trend in nucleophilicity within the halogens when a protic solvent is involved. The fastest rate of SN2 is observed for the iodide anion, and this is because this anion is associated with the weakest IMFs. The slowest rate of SN2 is associated with the fluoride anion, which is very small and highly charged. For this reason, it's associated with the strongest IMFs with the solvent. And what these intermolecular forces do is block the anion from engaging in a reaction with the electrophile. They surround and solvate the anion so well that it can't form a bond to any other species that might be in solution. Or if it does, it only does so very slowly. This is a nice example of a steric effect, but its origin really is in the intermolecular forces between the solvent and the anion. On the other hand, aprotic solvents solvate cations strongly, and this leaves the anionic nucleophiles that these cations come along with relatively naked. The key variable when it comes to nucleophilicity in this case is now the charge to size ratio of the anion, where smaller, a higher charge to size ratio, means a faster rate of reaction. So here, the order of nucleophilicity switches. When placed in an aprotic solvent, fluoride is most reactive, followed by chloride, bromide, and iodide. And this is to some extent more consistent with our expectations because it's consistent with pKa values for the conjugate acids of these ions, HX. HF is the weakest acid, HI the strongest acid in this series. So this is the nucleophilicity order we would expect on the grounds of pKa. In that sense, it's sort of normal, and the reason it comes out, quote, normal like this is because of the comparative lack of engagement of the solvent in the aprotic case down here. In the protic case, the solvent gets involved intimately with the nucleophile.